Okay, so hi, this is Jay and Sedef here from VMware. We're going to talk about uh, how these CNI plugins work and how you can look at what's happening packet to packet to understand if you're having issues with CNIs or network policies or other networking related stuff in your pod and service networks and Kubernetes. So Sedef's going to start us off and then we'll get to a demo in a little bit.
Hello everyone. So we will start with introducing some Kubernetes networking concepts and then go into detail about how CNIs are providing connectivity. And we will conclude with a packet level walkthrough. So in Kubernetes, networking is a combination of many concepts, and it is important to know them to troubleshoot any connectivity problem. So pod-to-pod networking is provided by third-party CNI plugins. And since pods are transient, Kubernetes has an abstraction called services, which allow us to reach a group of pods using virtual IPs. And kube-proxy is enabling connectivity to services by using load balancers like iptables. And how you find services is also part of networking. There's Kubernetes DNS service that provides that. Once you get basic pod-to-pod service connectivity, how you secure your applications by isolating them is another networking aspect, and CNI plugins provide this as well. The last aspect is how Kubernetes handles external traffic. There are several ways to do it. For example, layer 4, layer 7 load balancers, or using node-port Kubernetes construct. So out of these 5 concepts, in this talk, we are gonna mostly talking about CNI plugins. Okay, let's start with CNI plugins. So Kubernetes adopts CNI model to interact with third-party CNI networking plugins. These plugins are responsible for IP assignment, connectivity, and pod security. Every time a pod is initialized, CNI is being called. It creates a pseudo interface, assigns it an IP, and attaches it to the underlay network. And when pods gets deleted, CNI is again being called to clean up the resources.
So the CNI API is pretty simple in terms of what CNI supports, because all it has add, delete, check. It's a relatively simple API in terms of what needs to be called in order to launch a container. But it is a separate API that's managed by a separate group. Yeah.
Yes. Go on. And let's go over some traditional Linux constructs that are used by most of the CNI plugins to provide connectivity. First one is link network namespaces. So they provide a separate instance of kernel networking stack, like different set of interfaces, routes, firewall rules to isolate processes. All pods and hosts are sitting on different network namespaces. In this diagram, we have a single node. We have 2 pods, and you see all of them are sitting on different network namespaces. And to communicate between pod network namespace and node host network namespace, we use a Linux network construct called wheat pairs. Here you see ETH0 and wheat A is one wheat pair, and the other one is this one. And they are nothing but patch cables. What goes in one end comes out the other. We also want pods to talk to each other and use a very familiar construct called Linux bridges. So it is a networking switch. It is nothing but a switch and does layer 2 forwarding. Also, when our pods wants to communicate with the host and host wants to communicate with the pods, route tables comes into picture. So here you see everything that is destined to pod siders will be sent to bridge, and bridge knows how to forward them. As I mentioned, hosts and nodes are sitting on different network namespaces, and they have different route table rules, as you can see here. So we looked at how pods can communicate with each other in a single node. When there are multiple nodes, there are different networking approaches CNI offer. We can categorize them as non-overlay and overlay networking approaches. So the first option in non-overlay networking is layer 2 networking. When the nodes are in the same subnet or VPC, virtual private cloud, traffic can be routed using L2 networking. Another option is providing a pure layer 3 networking. So this option requires some configuration in the underlying network. So it is only suitable if underlying network can be controlled. So this is mostly possible in maybe private data centers. And there are several ways to achieve this. Calico uses BGP, or private data centers may implement their own CNI to provide layer 3 networking. And then when our nodes are not sitting on the same subnet, or we don't have any control on the underlying network, there is overlay networking option where packets gets encapsulated so that underlying network doesn't have to know anything about path siders. And there are several encapsulation methods that can be used for encapsulation. And the last one is hybrid mode. Whenever, so since there is encapsulation and decapsulation process in the overlay network, there is some overhead. So to avoid this, hybrid mode comes into picture. We encapsulate packets only when it is necessary. And Entry and Calico both supports this hybrid mode as well.
Yeah, I'll just quickly say EKS is, we're going to go over EKS, Calico, and Antria in a little bit, and you'll see the differences. But, you know, in EKS, you don't need an overlay if you're using their CNI because of the tight control that they have over IP addresses and being able to use ENIs and stuff. Other CNIs, you know, use those overlays. Keep going.
Yeah, so we mentioned we need encapsulation for all overlay networking. So let's have a look at how encapsulation works. CNI has support for several encapsulation methods, but let's look at two of them here, IP in IP and VXLAN tunneling. So basically what happens is source node encapsulates network packets in another header so that underlying network can route them without knowing pod IPs. So for example, in IP tunneling, you see this is the IP header which has pod IPs, and it gets encapsulated with another header with node IPs, so that underlying will only have to route node IPs. So when you capture the packets using Wireshark, and when you check those packets, you will see two IP headers in the packets. And for VXLAN tunneling, Ethernet frames gets encapsulated into UDP packets. And again, when you see the Wireshark packet capture, you will see the Ethernet packet, and on top of it, there will be a UDP packet, basically. Okay, now we are gonna briefly mention how some CNIs are providing networking at a high level. So it is important to know underlying constructs your CNI is using to better debug connectivity issues. Let's start with Calico. Calico supports multiple data planes like standard Linux networking or Linux eBPF and Windows networking. Also, it has three networking flavors. It supports pure layer 3 networking where traffic is not encapsulated. For this, it uses BGP route sharing, and underlying network needs to support BGP as well and set up underlying routes accordingly. Otherwise, this is not an option. It also supports overlay network option, supports both IP in IP and VXLAN encapsulation. Also, it has hybrid mode, and uses layer 2 networking for if the nodes are on the same subnet, and uses overlay for different subnets. We are not going to go into detail of these CNI architectures. It is out of scope of this talk. Let's talk about another CNI called Antria. So Calico did not have any bridge in its while doing networking. But here we see a virtual bridge that is being used, pretty similar to Linux bridges. It routes traffic using multiple flow tables and supports both Windows and Linux. If you look at the diagram, pods.
Quick interruption. When we talk about flow tables, so Open vSwitch is the backend for, like Sedef mentioned, Antria, and so Open vSwitch is based on these flow tables, and that's the whole way that you architect a network in Open vSwitch compared with, you know, what Calico is doing in the last slide with just using BGP for the routing. I just wanted to repeat that.
Right. Yeah. And if you see the diagram here, we have two pods. They are connected to OVS bridge using wheat pairs. This part is the same with regular Linux architecture, but on the OVS bridge itself, we are seeing a gateway 0 port, which is the gateway of the node subnet, and TAN0 port, which is the tunnel port that is used for creating overlay tunnels between nodes. And Antria is also supporting overlay mode. It supports many different encapsulation techniques. It also has support for hybrid mode, where it uses encapsulation only for the inter-network traffic. So we are going to see.
Yeah, we'll actually see when we look at the Antria stuff. We'll see that all the traffic actually flows into that into that gateway, specifically, even local traffic, which is interesting from a control and security perspective. Yeah.
Right. And one important difference here is that network policies are installed by OVS flows instead of like Calico using iptables eBPF. So here we are going to show some examples of non-overlay and overlay routing. So here we are seeing non-overlay, where we do not encapsulate packets and use regular layer 2 networking like ARP and route entry. Here we have two pods that are connected via a switch that is to demonstrate they are sitting on the same L2 network. And these are the subnets of the pods inside nodes. So when pod 1 wants to talk with pod 3, it sends traffic through the wheat pair, hits the bridge. Bridge knows that it is not destined to some pod in this node. Hence, it sends traffic to the route table. In the route table, so every node's pod sider is known in the route table. So here you see 172.16.1.0/24. Every traffic that comes to the pod sider of this node has to be sent via ETH0 device, and next stop for those packets will be this one. So will be the node to IP.
When you just literally run route-n in your Linux terminal, right? Every Linux operating system has one of these routing tables. So this is a command anybody can run at home if they want. Yeah.
Yes, and after it is route tables, the packet will be sent through ETH0 and routed using standard layer 2 networking, and then arrives to the second node. And when it arrives, it is gonna again check the route table, and every packet that is destined to the pod sider will be sent to bridge BR0 interface in both nodes. So the packet will arrive BR0 bridge, and bridge knows where to forward it, through which wheat pair it should forward the packet. And hence, this is how it works in the same subnet, non-overlay networking.
And in Calico, you wouldn't have that bridge, right? So if you would just have, it would just go straight from the routing, you'll hit the Linux kernel, and the Linux kernel says, okay, I know exactly how to get to that IP address, and it'll have it attached.
Exactly. So this actually is a good point. This example applies to both Calico and Antria, except that Calico, instead of having a bridge, has more route table entries.
We'll see that.
Yeah. And So yeah, if for example a non-overlay network is not an option for you because you are sitting on different subnets, or you don't have any control in the underlying network and cannot do layer 3 networking, overlay is the way to go. And encapsulation can be done in many ways. So you see, the only difference between this picture and this picture is this one has tan0 interfaces that is used to encapsulate packets. And you see there's a change here too. We added a router here to demonstrate that this is not a L2 network, but it is a layer 3 network. This can be the internet or private or public clouds. So here again, when the pod 1 wants to communicate with pod 2, it will hit the bridge, then it will hit the route table, but in route table there's a difference. So every packet that is destined to the other node's pod sider is gonna be forwarded to tan0 first.
Yeah, so on the left, I've said this before, but just to repeat again, on the left is that's your cloud stuff, right? That's your EKS, that's your GKE, that's your, if you're using something like an NSX or something like that, you can have this fancy non-overlay stuff set up for you using hypervisor native network tooling. On the right is typically when you're spinning up your own clusters, that's when you're using a CNI provider that will kind of abstract that all away for you and using an overlay, you know, for people that don't have a whole lot of experience with this stuff.
Right. And yeah, the packets will be sent to tan0, and there's a process attached to this tan0 interface that encapsulates the traffic. So it adds another header with node IPs on top of the pod IPs and sends it over the underlying network. For underlying network, it is simply a packet that is destined from node 1 to node 2, so it knows how to route it. Packet reaches to node 2, and then it gets decapsulated, sent to the bridge, and reaches to its final destination. So now we are going to see a packet walkthrough for whatever we explained.
Okay, so here we go. So the first thing that we're going to do is go ahead and hit play. Sedef, I don't know if it's playing or not.
Yeah.
Yeah, so first thing we're going to do is run ARP, which Sedef mentioned a little while ago. So we can see there that you might want to pause it. See there that, oh. Oh, yeah, go ahead and just keep it running the whole time. Don't worry about it. Okay, yeah. So once we run ARP, we can see all the stuff that's locally available. I think like the what's it called? So the local pods and the local nodes. So once Sedef hits play, now we're going to see it again. Okay, cool. Yeah. So and that this isn't a Calico cluster. I'm going to swap back and forth. The blue terminal is Android, the black is Calico. And then there's another black terminal that's EKS as well. And I'm just going to jump around and show you the commands here. So, yeah, so we do that. And then we can see that there's these 100 IPs and there's these 192 IPs. The 192s, those are the nodes. Now, if we run IPNet NS, we ran it really quickly, but you can see it again here, right? We don't see it in EKS, which is interesting. I'll leave that as a homework assignment to the viewers here. Why my EKS cluster didn't show me any network namespaces. But CNI provide the CNI network namespaces. In here, you can see that the 4 pods, the 100 pods, all have a CNI network namespace. Now, turning TCP dump on, now we can jump in and we can see that there's some traffic going from that 64.0.1 to our 100.198. We jump to the bottom, and then we can see that the IP address, that 198 IP address, so by the way, that TCP dump is tracing one of those Calico interfaces. So you do TCP dump -I on one of the outputs of, like, for example, the IPA command, and then you can trace the exact traffic going into that interface, into that pod and nothing else. So, okay, so we can see that that 198 is actually core DNS, makes perfect sense. Core DNS is constantly chatting with the API server, trying to figure, with the Kubernetes API server, trying to figure out endpoints and stuff like that. Um, so there we go. Now we can do iptables save, and then we can go look and see how that routing happens, right? So we can see here there's a routing rule that's going to send anything to 164.0.1 to the Kubernetes service rule -npx, right? So the easiest way to do this, if you're not good at iptables like me, is you just say iptables save into a text file, and then you just jump around, and you can use star when you're on top of a word to jump from one chain to another, right? From one rule to another. So literally, so you go ahead and hit star, and then it takes you right down to kube service, and then you can see the comment there. That's the Kubernetes API server service. Now we're on a Tanzu mission control cluster here, which means our API servers are cluster API powered. They're running on host port. Our API servers on host port, and so we've got the API server running on a node local network 192.168.5.156, and we can see that kube service endpoint rule that the service pointed to actually finally forwards you to 192.168.5.156. And if we go and we get our node IP addresses, we'll see that corresponds to the control plane node. So this is just one example of how how you can trace through a packet flow from a pod out to the host network. There's a million other use cases you may want to trace, for example, pod to pod or whatever, but it's essentially the same logical series of steps that you can go through. And it would be the same in Antria as well, or any other CNI provider, because the kube-proxy is going to basically have to do roughly the same thing. Do keep in mind there are different ways to do kube-proxying, and there's some systems may not use iptables. There's IPVS and other things, other technologies. We've gone the simple route, though, taking those for granted. So, okay, now next, looking at the Antria thing. So we can see here the output was a little different, and I jumped over to EKS, but you can see now in EKS, all the gateways are 0000. Now back to Antria, you can see the output the Antria gateways are 000, Antria GW0. Let's just keep going. I think we're going to show it again later, Sedef. It's not a big deal. Okay. So yeah, anyways, so here we are now, and what we're going to try to do is we're going to try to we're back on our Calico cluster, where I'm going to make a daemon set. So that means I'm going to have an Nginx pod in every node, right? And I'm going to save the iptables rules, and we're going to show you what vanilla routing you just get for free that you have to kind of start. There's a few iptables rules that we use as a baseline that get created after you create a pod. Okay, these are just generic. They're just being created for us by Calico. The thing to note here is that they're all named. They're all being added to the -A Kali-TW-Calic 418EE. That's the interface name. Ignore the comment. The name inside the comment is a Calico specific thing to do comparison between which version of the iptables rules was being written. So it's a CNI specific thing they need. But if you want to look at the rules it's making for a given pod, you can look at the -A, what it's being appended to, right? So that's the change being appended to. Now we can see the pods are up. Now we've saved that file, and then the simplest, stupidest thing you can do to figure out whether your network policies are working correctly in Calico and is going to be well, first we need to make our policy. So yeah, okay. So we kubectl create. This is a network policy, and that network policy is going to deny traffic to those Nginx pods. And we know that we're going to see that network policy for sure on this node, because this node, it's a daemon set, which means one of these pods is running on every single node in our cluster. So we're definitely going to see it. And now let's see what the difference is between our last policies and our new policies. So we just get diff, and now you can see we've got a few different lines here, and we can see that there are some network policy stanzas, return of policy accepted, drop of no policies, pass packet, et cetera, right? So those are going to get applied after the pre-routing stage. And I'll show you briefly later that this doesn't change your service level routing. Your kube-proxy routing to your pods and all that stuff still works just the same. The only difference is that packets are being dropped once they get routed to the pods. Now, okay. So let's see here. Yeah, here it is. So this is, so if you've never seen these before, you see these decimals, this is how load balancing is done from the kube-proxy level. That's how it decides exactly which pod is going to get traffic from a service, right? Because obviously you may have 10 different pods behind a service. In these clusters, I've scaled up the amount of core DNS replicas so that we have plenty of examples of that. Again, now we jump over to the Entrea here in blue, and we've got, okay, namespaces. Okay, so yeah, so we show the namespaces, and then we delete everything, and then after we deleted this stuff, we just go ahead and recreate it. I'm not going to do the whole diff thing. I assume it doesn't matter as much this time anyways, because we're not mangling as many iptables rules. We're using Open vSwitch for security in Entrea. So the Entrea plugin, once we create that daemon set and the policy, well, we haven't created the policy yet. We can see these 3 rules if we look at table number 90. So you exec into the Entrea containers directly if you want to see this stuff, and you can run OVS, OFCTL dump flows, br-int, and that's essentially the equivalent of like looking through iptables in Open vSwitch. It's like the same, it's the equivalent kind of operation, right? You can look at those individual flows. And so now we've created the daemon set, and we've created the network policy. And once you look at the once you look at the network policy, you could see we briefly showed you there's an extra row in there, and that row shows the reg 1, the packets getting marked for getting dropped and whatnot out of that flow table. So that's how you can see those policies being applied in Entrea. And I think that's it. We made it.
Thank you for watching.
9 minutes and 38 seconds. Okay, great. So yeah, that's pretty much that's pretty much our story. So please do reach out to us. I'm JUnit100 on Twitter, and Sedef is, I don't know if Sedef has a Twitter account, but
Nowhere.
yeah, but we're easy to find.